Hello, in this video I'd like to work out the gravity inside a hollow sphere. This isn't the easiest way of doing this. There are much easier ways of working out the gravity inside of a hollow sphere, but there's some really cool integration things that wind up happening when you solve this problem in this really ultimately kind of gross way. So let's have some fun. Let's do some really messy integrals. And let's work out the gravity inside of a hollow sphere. So here we have our hollow sphere. I'm going to say that we have, imagine this is in 3 dimensions, and we filled in the space between these two spheres with matter, and that matter has a gravitation that's coming from it. And then we're interested in finding how that matter affects another piece of matter located somewhere within the sphere. Now, without loss of generality, we can say that this point is, let's say, 1 unit up in the z direction. And of course, we anticipate that this object here is not going to be pulled in the x or y directions. It's only going to be pulled in the z direction, either upwards or downwards, or maybe it's not going to be influenced by gravity at all. But we're only interested in the force on this object in the z direction. So this allows us to save ourselves two integrals, right? Working out the x and y components of the gravitational force if we just pick this particular point of consideration. Of course, you don't have to pick one, but like just by doing some rescaling arguments, without loss of generality, we can pick a z-coordinate of 1 for our z-coordinate. And of course, if you wanted to, you could throw another variable in here to represent the z-coordinate of the point in question where we're trying to figure out the gravitational field. But that's just an extra variable. It's going to make all of the actual integration just that much trickier without really gaining anything. So here we have this point. Now let's imagine a little piece of matter as part of the spherical shell. So that matter is going to have some mass associated to it, and it's going to be applying some gravitational force to this point. The magnitude of that gravitational force is going to be so let's call this distance d. It's going to be gmm over d squared. And the mass of this, so the mass of this point will let be little m, and the mass of this point here will let be big M. The mass of this point here is going to be the density of the spherical shell times dV. Right, if we imagine this tiny little point here, it's having corresponding to a tiny piece of volume dV, it's going to have mass, the density times its volume. So I'll use delta for the density of the matter times V, the tiny piece of volume that this point corresponds to. Now, of course, that isn't exactly what we're interested in, and we also don't quite know what d is. Ultimately, what I'll want to do is I'll want to do this integral as a spherical integral. So that means that, hold on, let me make sure I'm getting this right. That means that the coordinates of this point, I'm going to want to use spherical coordinates so that my bounds of integration are nice and simple. The coordinates of this point are going to be rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. So those are the coordinates of this particular point here. And what we're going to have to do is we're going to have to use that to work out what this distance d is, and then we're also going to need to work out what this angle is here, so that we can work out the component of this force, right? this gravitational force is going to be going in this direction, but we only care about the z component of that force, not its magnitude, because we specifically don't care about the x and y components of the magnitude of this force. So we need to worry about this angle, we need to worry about this distance. In order to figure those out, let's sketch out this particular triangle here, slightly larger. So this angle here, from directly vertical to our point, we call phi, right? That's spherical coordinates. Phi is the angle from the North Pole. Maybe you have slightly different spherical coordinates, but that's the spherical coordinates that I'm working with for this problem here. And then we want our point mass that we're trying to figure out what the gravitational force is on is here, 1 unit up. This distance here, the distance from the center of the sphere, so this point here is the center of the sphere, the distance from the center of the sphere to our point mass up here is going to be rho. Right, that's what rho represents in spherical coordinates, is simply the distance between the center, the distance between the origin and the point in consideration. So this is our rho. Doing a little bit of trig. This distance here is rho sine phi. This vertical distance from here to here is going to be rho cosine phi, and so this vertical distance from here to here is rho cosine phi minus 1. So that's this vertical distance here between the vertical distance between this point and this point. And then we can sketch in our diagonal line that I drew here. This is our distance d, and we have to figure out what that distance is. Lucky for us, well, we can work that out. There's two ways of working this out. One is to use the law of cosines on this triangle down here, and the other one is to just use the Pythagorean theorem, right? This distance d squared is going to be equal to this leg of the triangle squared plus this leg of the triangle squared, which is going to be rho squared cosine squared phi plus 2, whoops, there's a minus sign there, it's a minus 2. Right, this bit here is this leg squared. And then, of course, we notice that sine squared phi plus cosine squared phi is equal to 1. So this bit here is just equal to phi squared. So d is going to equal the square root of rho squared plus 1 minus 2 rho cosine phi. You get exactly the same answer if you use the law of cosines in this case. So that allows us to work out exactly what the formula for d is. And you might think, oh, this actually works out quite nicely because we have a d squared here. But not quite. Remember that we're not interested in integrating the magnitude of the force. We're interested in integrating the z component of the force, which I'm going to write as f, just so that it's clear that we're not taking the partial derivative with respect to z. I'm going to write it as fz, which I don't know if that makes things better or worse. The notation in Calc 3 is a little bit inconsistent from source to source. But this is going to be the z component of our force, the thing that we actually want to add up. And this is going to be our force, gm delta dv, divided by d squared, times the cosine of this angle here, which is this angle here on the diagram. Let's call this alpha. And luckily, we happen to have a right triangle that has alpha as one of its angles, so we can work out exactly what the cosine of alpha is. The cosine of this angle here is going to be rho cosine phi minus 1 divided by d. And oh, unfortunately, we now have a d cubed in the denominator, so it doesn't quite work out as nicely as we hoped. But this is the thing that we want to integrate, and let's set up those integrals. So we are interested in adding up all of these tiny pieces of matter that make up this spherical shell and the gravity that they contribute, the force of gravity that they contribute to this particular point here. So what we need to do is we need to integrate, again, over this spherical shell. That's going to be the integral from theta equals 0 to theta equals 2 pi. Right? Those are the bounds of theta. Theta isn't involved here, so it's actually going to just work out as a multiplying by 2 pi at the end. The integral from, hold on, I want to do these in the right order, rho equals a to rho equals b. And again, it doesn't really matter where we start or end the shell. We'll see that things work out very nicely regardless of our choice of A and B. So we can be a little bit loose here. And then finally, from phi goes from 0 to pi. Of this thing that we're trying to integrate here, let's get the constants out front. So that's going to be g m delta. And then we want our rho cosine phi minus 1. I'm actually going to start a new line here just so that everything's clear. So this is going to be rho cosine phi minus 1 divided by d cubed. So that's going to be, I actually want to, so that's rho plus 1 minus 2 rho cosine phi to the power of 3/2 times dv. And remember, we're in spherical coordinates now, so we can't just integrate d rho, d theta, d phi, or whichever order you want. We need to add in the Jacobian term. And the Jacobian term for spherical coordinates, when you set up your spherical coordinates in this particular fashion, happens to be rho squared sine phi. And then we have our d phi, d rho, d theta. So this is the integral that we're trying to evaluate here. Oh, it's quite gross. But it turns out that we can actually solve this integral fairly simply using u-substitution. And actually, we already know what our u is. So this actually works out, this works out pretty well. So let's do this. Let's say that we want to integrate from phi equals 0 to phi equals pi with this particular really gross formula here. Just so that I don't have to write dd, I'm going to call this thing u. So we're going to have u is equal to rho plus 1 minus 2 rho cosine phi. And remember that we're just integrating this d phi. So for the moment, we can treat rho as a constant, which is very nice. So this is going to be, let's see, so du is going to be, this is a constant, so this is negative 2 rho, and then actually it's going to be a positive 2 rho sine phi. And we happen to have a rho sine phi here, so that's good. And then this rho cosine phi minus 1, we can actually extract from this u just by throwing in some rows in there. And again, remember, rho is a constant, so we don't have to worry about that messing up our integral just yet. Let's see. So we have that 2 rho cosine phi is equal to rho plus 1 minus u, right? I'm just rewriting this formula here. And then we want to divide by 2. So that's going to give us our rho cosine phi. And then actually we want rho cosine phi minus 1. So we're going to subtract 2 over 2, and that's going to switch this to a minus 1. There we go. Let me check to see if this agrees with. Oh, whoops. That's the fun part about doing these really long derivations, is that every so often you'll forget something, and then you can go back and try to trace it through. So here we have, and this is, in fact, yes, this is what I want. Okay, so this is our rho cosine phi minus 1 is going to be this term here. And now I want du over 2 is equal to rho sine phi. And now I can put the pieces together. So here I'm interested in integrating. Let's see, this is going to be, so this term here gives us this. This denominator term gives us u to the negative 3/2. This term here is a rho times du over 2. And then we'll deal with d rho, d theta later, and we'll also deal with plugging in the bounds for phi later, once we do our u-substitution and then convert everything back to being in terms of phi. So I have this thing that I want to integrate, and it looks kind of gross, but really all we're looking at here is kind of a polynomial. The exponents aren't integers, but otherwise it's a polynomial. So what we have here is going to be the integral of, so we have a u to the negative 3/2 term times rho squared minus 1 all over 2. And then we also have a u times u to the negative 3/2, which is u to the negative 1/2 term. And that gets multiplied by a negative sign here, which I've copied down there. And it gets divided by 2. Oh, whoops, I forgot this 2 here, which also goes here. Let's see, so this is u to the negative 3/2 times negative u divided by 2 divided by another 2 multiplied by rho. And then this integral here is going to be u to the negative 1/2 times negative 2 times this. And then this term here is going to give us a u to the 1/2. And then we have to multiply by 2. And then we'll eventually need to evaluate this between our bounds. But let's convert it back to being in terms of phi before we do that. Now, this here looks kind of gross, but we can actually rewrite it using our identity for u. this term here is going to be, we can write it as u to the -1/2 times, so u to the 1/2 is u to the -1/2 times u. So this is going to be, let's see, negative, cancel the 2 and the 4 to get -1/2, rho cubed minus rho in the numerator. And this is -1/2 rho times u. And then this u here, we can fill in. And we can actually cancel out a whole bunch of terms here. Or actually, we can combine like terms. We get a rho cubed and another rho cubed. This is going to be 2 rho cubed. We have a minus rho and a plus rho. Is that right? And so our antiderivative of this term here with respect to rho is going to be rho squared minus cosine phi minus rho cubed, all divided by the square root of 1 plus rho squared minus 2 rho cosine phi. And of course, we need to evaluate that from phi goes from 0 to pi. And then, of course, we need to, multiply by the GM delta, and then take the integral from rho equals a to rho equals b, and then take the integral from theta equals 0 to theta equals pi, but we'll do that later. For now, we need to take this antiderivative that we got and evaluate it from phi equals 0 to phi equals pi. When phi equals 0, this is going to be, when phi equals pi, cosine of pi is -1. So this is going to be rho squared times -1, so it's negative rho squared, minus rho cubed, divided by the square root of 1 plus rho squared plus 2 rho, which you might recognize as 1 plus rho squared. And then we subtract off what we get when phi is equal to 0. We get, so cosine of 0 is equal to 1. So this is rho squared minus rho cubed divided by 1 plus rho squared minus 2 rho. You'll notice that this is 1 minus rho quantity squared. Or we should actually write this as rho minus 1 quantity squared. So this is the value that we get. And here's the cool part. Here's the part why I made this video, is because we have the square root of a square. And naively you think, oh, well, that undoes it. But not quite. It gives us an absolute value. So this is the integral, and then again, we need to multiply by GM delta, take the integral from rho equals a to rho equals b, take the integral from theta equals 0 to theta equals 2 pi. But here's the clever bit. Because our a and our b are both larger than 1, let's assume for the moment that this point here that's 1 unit up on the z-axis is, as we've drawn it, actually inside the hollow sphere. Then that means that a is at least 1 and b is at least 1. So when we're taking the integral of this, d rho, we can assume that rho is greater than 1 when doing this calculation. And so that means that, well, of course, 1 plus rho is going to be positive, so we don't need these absolute values. And Rho minus 1 is also going to be positive, so we don't need these absolute values either. And now we do a little bit of polynomial arithmetic. This is going to be, this here is negative rho squared, right? If we cancel out a 1 plus rho from the top and bottom, we'll get a negative rho squared. And then if we cancel out a rho minus 1 from the top and bottom here, it's in the wrong order, but that's okay. We will get a positive, so here we get a negative rho squared, and then there's another minus sign, so we get a positive rho squared. Ah, you see where this is going now. This gives us 0. So even when we multiply by gm delta and then take the integral from 0 to 2 pi, which is really just going to multiply the answer by 2 pi, we're going to get 0 for our gravity that's affecting this particular point here. So that's the cool thing. Of course, you're welcome to go ahead and you can use exactly the same formula that I've shown you here to work out the gravity where the hollow sphere is actually here, closer to 1, right? Where A and B are both smaller than 1. In that case, you need to replace the absolute value of 1 minus rho. Well, or the absolute value of rho minus 1 is going to be 1 minus rho, right? There's going to be a minus sign introduced there because rho minus 1 is going to be negative. So you need to take the negative to when you take the absolute value. And then you actually get some sort of non-zero term, but you can integrate that. And that gives you, it actually works out that if the hollow sphere, if the point is on the outside of the hollow sphere, then it acts gravitationally as if it was just a point mass, just like a regular sphere does. So that's the gravity inside a hollow sphere. It's a really gross integral to do, but sometimes it's fun to do really gross integrals. I enjoy doing a good gross integral every now and then. And ultimately, we get this really cool absolute value thing that allows this denominator term, under the assumption that rho is greater than 1, to cancel. And if rho is less than 1, well, again, it won't cancel. It'll give you, it'll still work out fairly nicely. And then, of course, you have to multiply by gm delta and then multiply by 2 pi. And again, it gives you the gravity of a point mass. So I hope that was fun, and I'll see you in a future video.